得可以吗？我觉得可以啊，不需要买，完全不拿那个电的。我不知道，这个应该可以。
All right. So just to start, the convention I always used seems to have caused some confusion. So possibly to add to the confusion, I just wanted to repeat what I said yesterday about kinetic energy-driven and potential energy-driven superconductivity. So there are two ways that you can define kinetic energy. Right? One is if you just think, for example, about 3 electrons, say, that the kinetic energy is more or less this. Right? So this thing, you will notice, let's say if we write it in the first quantized notation as a sum over all particles, is not negative. So if you have a ground state with some number n of particles, and you neglect potential energy, then you just minimize this. Right? So here, if you now add superconductivity to this non-interacting ground state, you change the wave function in some way. So you move it away from the configuration that minimizes this. So the kinetic energy increases.
Sorry, so this is a BCS ground state projected onto the...
Wait, so this is just the simple thing I talked about yesterday. It's just the BCS theory of an interacting electron gas. So you start with the non-interacting limit, where you do your Hartree approximation, neglecting BCS in the other channels. You optimize this, you get some value for the kinetic energy. Now you do the calculation again in a BCS ground state that's different from the state that optimizes this. Therefore, whatever expectation value you get from this is going to be bigger.
No, I'm asking about ensembles, because the BCS, that KE business is you've taken n particles. Say.
Wait, this is an operator.
Okay.
So this has nothing to do with ensembles. This is an operator.
Okay.
All right. So I've written it here in first quantized notation. You can write it in whatever you want. All I'm saying is that the expectation value of that operator changes. Yeah.
So here, can I assume potential energy is just minus some content?
At the moment, we're assuming that it's 0, right? We're doing the simplest Hartree approximation. So
But BCS.
wait. So I'm sorry. So we start with only with the non-interacting ground state, then we get something. Now we add to this a BCS Hartree approximation to some potential energy. If that gives us a superconducting ground state, that's a new wave function. We evaluate the expectation value of the kinetic energy operator using that wave function. We get a number that's bigger. That's all. Okay? So in that sense, you would say that you have potential energy-driven superconductivity because the total energy has to go down if it wants to be superconducting. This guy is moved away from its optimum. It goes up. Good. Now, in general, you don't want to define the kinetic energy this way. You want to put the chemical potential into the problem. And I almost never write the chemical potential explicitly. I just fold it into the energy, whatever the energy is. But here I'll make it explicit. Right? So this is the situation where you have a partly filled bed. I don't want to make any particular statement about what this is. It's just, some function in K-space. I have a chemical potential. To make the non-interacting ground state, I fill up all the states up to the chemical potential. All right? So then, in this definition of the kinetic energy term, right, it's negative. You gain energy by delocalizing because I've subtracted off the chemical potential part. All right? So if you take your favorite, for example, tight binding model, you fill it partially full up to the chemical potential, you evaluate the expectation value of the band energy, you get a negative number. Actually, it starts out at 0. If you have an empty band, it's negative, and then it goes back to 0 when you have a full band. Right? So it expresses the energy gained by delocalization. Right? This is much more natural for talking about solids. Right? Now we do the same thing. We move this guy off of its optimum. That means that the kinetic energy increases, so its magnitude decreases. Right? Because it starts life negative. It gets from more negative to less negative, so its magnitude decreases. Right? So this is supposed to be a complete triviality. This is just two ways to express, two conventions to express the same physics. This lower one is the one that I find much more useful. Right? And that's why it's useful to say that the magnitude of the kinetic energy goes down. So if you do, for example, a calculation in a tight binding model, all right, and then you just evaluate, you take your favorite nearest neighbor tight binding model, you fill it partway up, you evaluate the expectation value of the EK term. Then you do the same again with a BCS wave function, you find that the expectation value of the EK term gets less. That is to say, gets more, meaning that its magnitude gets less. All right. But it's just rephrasing the same physics, that you're taking your kinetic energy operator and moving it off of its optimum. Okay, so now I want to come back to where I left things yesterday. We had started with a very simple Hartree-Fock kind of model, all right, in which we said that for singlet BCS, we had an interaction. Let's take for the moment Heisenberg symmetry. Do I have the spin labels right? Yes. Okay, so now what we want to do with this is minimize the energy. So we have a Hamiltonian. Which is this. Right? And now I want to solve the Hamiltonian, recompute this, and make everything self-consistent. That's what you do in Hartree-Fock. Right? So let me define
Andy,
yes,
sorry with my conclusion. Is it singlet or triplet?
singlet, I believe. That's why we have the 3 here and the minus.
And these interactions in principle carry a p minus p prime.
Yes, correct. They have, not just in principle, but in practice. They're even, so it doesn't matter which way you write it, but it's like this. So in fact, this is where I was going with this. This is going to be So that gives you a Hamiltonian where this term becomes I just changed names from P prime to P. Okay, so so far so good. Now we all, so far so good. Now we all know that you can diagonalize this by a Boulder transformation. So you introduce, the convenient way to do this is to define a Nambu spinner, which I will write with a capital psi, index K, which is a two-component thing. Which I'm going to write like this. Okay? So then in terms of this object, I can rewrite the Hamiltonian as a diagonal matrix like this. Here, we lost the spin sum because there's an up here and a down here. And when you collect the various terms, that takes care of the spin. You have a minus here because the up-up component has a psi on the left, and when I take the complex conjugate transpose of psi dagger on the right, the down-down component has the psi dagger on the right and the psi on the left, so I have to commute them, and that gives me a minus sign. And then there's a constant term coming from the commutator, which I'm just going to throw away. It's not important for my considerations here, although it will be important if you want to compute, for example, the total energy. Sorry?
That was my comment.
Oh, okay. All right. Also, in this language, we can re-express my friend, sorry for that illegible scrawl, psi down up of P, which is expectation value of psi P up, psi minus P. Oops. Psi P down, psi minus P up. And there's infinite possibilities to make sign mistakes by getting your operators out of order or being slightly inconsistent with your dimensions about up and down here. And I hope I did everything right. Okay, and this thing you could rewrite as the expectation value of psi dagger, the matrix 0, 0, 1, 0, psi. All right? Because you want to get psi p down the way I did it. That means you want to pick out the right-hand component of the complex conjugate transpose, going with psi up. And the only other funny business that's happened here is that as I've defined things, this would actually be phi of minus p. Right? But we're talking about singlet superconductivity, which is even parity, so it's the same as phi of p. Okay. So, as you know, this is a quadratic Hamiltonian. It's just a 2 by 2 matrix. It has the eigenvalues that we all know and love from 2 by 2 matrices. Because this is just, we could rewrite this as EK tau 3, where this is a Pauli matrix acting on this space, plus. And here, let me assume, or choose the phase, such that delta dagger equals delta. All right? If I do that, then I can rewrite this as delta tau 1. So, as you know very well, the eigenvalues are just the square root of the sum of the squares. And in the basis that diagonalizes this thing, there's this eigenstate, which has eigenvalue minus ek, a negative number, and eigenstate 1, 0, eigenvalue plus ek. At a non-zero temperature, this would be the occupancy is the Fermi function of minus ek. Here, the occupancy is the Fermi function of its energy. So then, so if I just define R to be the rotation in this space that takes me from the eigenbasis to the starting basis, then I have two states. Psi, let me call it minus, which is R 0, 1. Psi, let me call it plus. R acting on 1, 0. So we may then make this self-consistency equation by saying that we have well, not trace, but and then finally, these guys are functions of delta, so to make the thing fully self-consistent, we must multiply this by the interaction. Sum over the interaction. That gives us the self-consistency equation, which is there. Okay. Right? So far, so straightforward. I assume that you've all seen how to diagonalize this. This is just games with 2 by 2 Pauli matrices. If I go over to here, you can find that so this is just the usual rotation in pseudospin space. If you stick this in its complex conjugate and ask that it diagonalize the Hamiltonian, you get this condition on theta. And then you can substitute that in here, knowing what the rotation matrices are, work out this whole thing, and what you find out is that and this is, of course, just delta over, I guess I wanted to call that P prime, didn't I? Okay, so this, just keeping track of all the signs, is the usual BCS gap equation. All right, so what do we learn? Basically, both of these guys are positive, all right? Because EK is positive, basically this guy is bigger than that one. So this whole thing is negative. And therefore, to make this equation work, since this square root is positive, this delta presumably has the same sign as this, you have two choices. Well, you have two, basically, sorry, we have a P here. P prime in fact. So what you have to do, because this thing is negative, right, is that you have to get the combination of the P prime integral here, and this combination of potentials to be negative. Right, so that you can make this be self-consistent with that. Right? So this is the usual rule. If I take an S-wave superconductor, if I assume that this doesn't depend on direction, really, in momentum space, right? Then the integral over momentum is more or less straightforward. It doesn't have anything to do with the sign. And basically what I want is the average of this over all momentum transfers to be negative. All right? If this thing is negative, then I can make the self-consistent equation. If it's positive, then it doesn't want to do that. So that's the basic statement that attractive interactions, negative V rho, wants to give you superconductivity in the S-wave channel. Now let's go back to this V sigma for a moment. If you remember from last time, basically what I said was that if you have a system that wants to be anti-ferromagnetic, right, then this V sigma wants to be positive, especially at the first neighbor distance, so that it will favor having opposite spins. All right, so let me now do that in a little more detail. Let me linearize this equation, all right, so that I want to just look for the leading temperature, the leading instability, all right? Then what I get is, let me just call this thing V. All right. This is just going to be hyperbolic tangent of EP prime over 2. Probably there's this factor of 1/2. And now we have delta of P prime divided by absolute value of EP prime. All right, and this is actually should be E prime over 2t. So what we see, and this is in absolute value, so what we see is that as usual this is dominated logarithmically by the region near the Fermi surface. We had a lost minus sign, and I want to get this thing to be negative. All right? So now let's go back to our symmetry analysis, starting first in free space. So if I say that this guy transforms according to some representation of the rotation group, then I have something like this. Right? So to pick out the angular momentum L harmonic, I should multiply this equation by the conjugate of my favorite harmonic. Right? And obtain an equation which is essentially so this is a logarithm, it's cut off by temperature. If I'm interested in near the Fermi surface, then actually I can just replace this constant by this thing, which is a function of the magnitude of P, by 1. I still have a minus sign. So this is what I'm looking for. All right? So my goal, therefore, is to get that object to be negative.
In R, is it tau Z or tau Y?
Sorry, this is, I'm sorry. This is tau y. In fact, this is tau, I wrote it as tau 2, because my notation is that 1, 2, 3 instead of x, y, z. Sorry, yes. So that my Hamiltonian here was epsilon k tau 3 plus delta tau 1, so you want to rotate about the one which is perpendicular, which is 2.
Just to make sure, on the whatever line, the v, p minus v prime
Yeah.
is vp minus.
Yeah, it's this whole thing.
Uh-huh.
I just didn't want to write the whole thing over and over again. Okay, so anyway, now I'd like to go back and just ask how do we get this thing to be negative? All right, so this obviously has some kind of expansion in spherical harmonics. Anytime I have a function if both of these guys are on the Fermi surface, in a spherically symmetric case, this is a function only of the angle between them. If I have something which is a function of the difference of two angles, I can make an expansion in Legendre polynomials. So I can write this as V0 plus V1 right? So this will have some expansion. Yeah?
Good question. So on that side, it should be summation over both p and p prime.
Wait, I'm sorry. So we got to here,
Yeah.
we
and then
restricted to the
project
Fermi
that.
surface, then to project out this, we
Yes.
averaged over P prime.
Yes, I mean on the right hand side, it should also be over p
Yes,
prime,
sorry.
p.
Yes. All right. So this has some spherical harmonic expansion. All right. So clearly, if we want S wave, then we just want the average over the Fermi surface of this thing to be negative. Right? That means that you have, on average, an attractive potential coming from both channels. Okay. Now, V1 is not relevant because this whole construction that we did was for singlet superconductivity. And if you transform as the L equals 1 representation, you're odd under parity, so you have to be triplet. Right? So the next thing we could look at is 2. Right? And so we may now ask, when is V2 going to be negative? What kind of potentials give us a V2 which is negative? All right? So, and that answer is as follows. Let me go back to this, which is some kind of potential that connects 2 points on the Fermi surface. All right? So let me write this by saying that, and because I'm in a spherically symmetric situation, this can depend only on the magnitude of this vector. So let me write the magnitude of this guy. All right? So what it is, well, let me write the magnitude squared because that's easier. That's going to be 2 P Fermi squared minus 2, 1 minus 2 cosine theta 1 minus theta 2, if I just adopt a coordinate system where the two vectors define a plane and I look at the angle between them in that plane. So that says that v is some function. I could rewrite this as this. Right? Because this is a function of 1 minus cosine theta. So in fact, if I'm allowed, I could be allowed to have things which are the first power, then I would have 1 power of the sine there. Right? So it's basically a function like this. So let me just expand this guy as a function of its argument, just to see what might be going on. Right? So this I could write as v0 plus v1 sine squared theta 1 minus theta 2 over 2 plus v2 sine fourth. Right? Now, if I re-express this through this, right? Sine squared theta 1 minus theta 2 over 2 is cosine theta 1 minus theta 2. So that's the L equals 1 harmonic. This carries the L equals 2 information. It also carries some correction to the L equals 1 because of here. So I'd like to ask, when do I get this guy to be negative? All right, what kind of function has this to be negative? So to do that, let me just ask, this is some function of theta. Let me ask where it's maximum. Right? So let me compute the derivative of this v with respect to this angle difference. Let's see, this is the dark side of the blackboard. Can you see this if I write? All right, so I take a derivative here, and I get v1. I get 2 sine theta over 2 cosine theta over 2 times 2. That's going to be 1/2 sine theta plus v2. And then I'm here going to get, I got a 2 sine theta right half. Here I'm going to get a 4 sine theta. One derivative of sine is cosine and sine squared theta. So I'm going to get So this guy can have extrema when theta equals 0 or pi, that's two wave vectors parallel or exactly anti-parallel, or if these two guys have opposite sign, right? And if these two guys have opposite sign, then I can have a theta star when cosine squared theta over 2 equals minus v1 upon v2. All right? So,
should that be sine theta over 2 squared?
Yes, it should. I'm sorry. That's much better. All right. So now, what does this mean? There's two ways to make this work. V1 is negative, V2 is positive, or V1 is positive, V2 is negative. So if I take V1 is positive, V2 is negative, that gives me an interaction which looks like this, as a function of sine squared theta over 2. Right? It starts off at some value, where I put the axis. If V1 is positive, it initially increases. If V2 is negative, then it has a maximum and goes down. So the case that gives you d wave is an interaction which can be repulsive everywhere, all right, but has a maximum in its repulsion somewhere between 0 and pi. Right? If you have that case, you have a negative V2, and then it will want to be superconducting. All right? So what does that mean? Because I can't draw in 3 dimensions, let me draw a 2-dimensional Fermi surface. Here's theta equals pi, right? we want the interaction to have a maximum somewhere between 0 and pi, let's say halfway, just to make it easy to draw. So we want the interaction to be most repulsive between those points and less repulsive at other points. All right? So why does that give us a sign change? If you go back to your d-wave gap function, plus 0 minus 0 plus, you see that what's happening is that the most repulsive part of the interaction is connecting the part of the Fermi surface where the gap function is plus to the part of the Fermi surface where the gap function is minus. So it's a sort of sumo wrestler trick of getting a minus sign by using the most repulsive part of the interaction, but making a gap function change sign. Right?
What's
So,
sumo about that?
well, the idea is that it's using the strength of the interaction to do the opposite of what you might think it wants to do. So it's taking the interaction where it's strongest and flipping it over. Okay, so in essence, that's why anti-ferromagnetic type spin fluctuations, right, which are strongly peaked at some typical wave vector like this, which might be, if this really ran from zone edge to zone edge, 0 pi to pi 0, pi, so that's a pi pi wave vector. Something which is peaked there and is most repulsive at that point can give you d-wave superconductivity. Right? So the intuition you should have is that d-wave comes from interactions which are repulsive but with structure. And the structure should be such that they're most repulsive for connecting things partway around the Fermi surface. All right? So is that clear? Are there questions about this?
I mean, this isn't just, like, you're asking how do you get d-wave? If we turn it around and say we have a repulsive interaction with structure,
Yeah.
then we could get d-wave, you know, PD.
Wait, let's be, we haven't talked about P yet, right? This entire discussion was built on the premise that we had singlet superconductivity.
Sure.
But I will give you S, D, G, whatever. Yes. So, what I asked was how you get a V2, which is negative. You could then pursue the analysis and ask how you would get a V4, which is negative. All right? And then you need an interaction with more structure. All right? Then it has to oscillate several times as you go around. Right? So you can also see why it's harder to get higher angular, it's more difficult to get higher angular momentum pairing. Right? It's somehow natural to have an interaction that has modest structure as you go around. It's natural to say this is one thing, this is something else, and there's a maximum halfway in between. Once you start putting more oscillations, of course there's nothing impossible about it. And indeed there's discussion, it's actually more in the P-wave channel, but that some of the heavy fermion materials might be F-wave, as it were, instead of P-wave. Right? But it's not natural. Right? You need to put a lot more structure in the problem. There's a natural structure which gives you a maximum sort of halfway around.
Sorry, if my maximum in the repulsive interaction occurred at some non-zero but rather smaller vector.
Correct.
Like then.
No, but I think you need both maxima and oscillations, right? Because you need the V4 to be negative, right? So I haven't gone through that analysis myself, but the question you're really asking is, suppose that I have V0 positive, V1 positive, V2 positive, and just V4 negative. What kind of interaction structure will do that for me, right? And I don't know the answer to that off the top of my head, but I'm reasonably sure it's a quite complicated one, right? Whereas the thing which gives you negative V2 has this relatively natural shape. Right? Again, that's not a proof, it's just a plausibility argument, and it's supposed to tell you roughly how you should think about these things. Yeah?
Why antiferromagnetic interaction is repulsive in the momentum space?
Oh, that, if you go back, that's what I discussed before. It's basically, if you just Fourier transform the real space argument I gave you, you want an interaction which is basically repulsive, right? So that at the nearest neighbor distance, right, in order to say that you want spins to be opposite, right? If it was attractive, then you would want spins to be the same, right? So in antiferromagnetism, you're converting repulsion into something good by flipping one of the spins, right? And if you just Fourier transform the statement that you want strong repulsion at a nearest neighbor, right? That's the pi-pi kind of wave vector. So that's why. Right? So that's the generic argument that antiferromagnetism gives you D-wave. And that in repulsive interactions, if you're going to do singlet superconductivity, D-wave and its cousins are the most plausible thing to do.
So between two electrons with the same spin, it's repulsive.
Yeah.
But with opposite spin, it's attractive.
Right. But so again, if you go back to the basic interaction was this, right? So you want the basic interaction to be repulsive, so that when you make the spins opposite, it makes the energy happy, right? So the statement is that a repulsive interaction at that distance favors having opposite spins.
That's the coefficients.
Yeah. All right. Now, you can of course.
Is that
Yeah.
so that's some of that depends on whether you talk about localized states or general states, like in stoner magnetism, you have repulsion when you try to go to ferromagnetic states.
Well, no. You can have a stoner antiferromagnet, just right. Stoner is just right. So you can decide which wave vector you want to put here. It's the same formalism. But basically, if you chase this formalism through and ask what interaction does it imply
Oh, I see.
for the electrons, you will find that it implies a repulsive interaction with the structure that I gave you. Okay, so we could do the same thing for triplet. You go back to here, you just do essentially the same thing. Actually, you go back to the thing that I erased. You play exactly the same game, except now what you're going to have is Dt if I just look, for example, at the up-up component of the triplet, and remember the arguments I gave you yesterday, were that if we're looking at the linear instability, it suffices to take one member of the representation. Right, so we could look at this one. You could look at the up-down m equals 0 one if you preferred, and you get the same answer. Sorry, this is a phi, and this phi is psi p up, psi minus p down, as I defined it last time. You can again define a delta. You now need to make a Nambu spinner like this. Note they have the same spin. And by the way, just as and so then you get a Hamiltonian, which is this for the spin-up component. Now we need a half. Before we had a spin sum, right, which soaked up the difference between k and minus k. Now we have a half here because we've counted psi and psi dagger twice. All right, and we would get another term with a similar half for spin down, which I don't have to write in this connection. All right. Now, just as an aside, there's no reason in principle why you couldn't have superconductivity in a fully spin polarized system. Right? All of this goes through if the interaction had the correct form. You had a fully polarized ferromagnet, it's sort of like spinless fermions. It could have D-wave superconductivity. I don't know of any cases that do that, but I know of nothing against it in principle, and indeed, Warren Pickett proposed this for some of the rare earth lanthanum strontium manganites back in the day, which have basically fully polarized ferromagnetic ground states. Now the A prime phase of helium-3 is a step in that direction. The A prime phase is a triplet phase where there's a preponderance of up relative to down, as I remember this. But it's certainly not fully polarized. Anyway, Andre?
One argument against superconductivity of two polarized state is that if you start with charge interaction and then start building speed interaction, then effective attraction between up speeds is due to the bubble of down speeds. And when you don't have down speeds, you don't have a bubble.
Right. Yeah. No, you will have to do something moderately unnatural to get an appropriate interaction. All right. So that's why I said there's no reason of principle. There are considerable reasons of practice. And to my knowledge, nobody's ever found such a thing. But it's an intriguing possibility, and maybe there's something that would do it. Right? As far as I can tell, there's no law of nature against it. One thing, actually I went too fast. Because this has the operators in an opposite order, there's a minus living there. However, in my unnatural definition, basically phi is also minus expectation value of this operator. So I believe if you use exactly these conventions, which I should have been more careful about defining before I got into this, you will find a minus here, just from the fact that I used effectively a different operator ordering and a compensating minus here. So all the same structure works out exactly as we had before, and we wind up with a self-consistent equation, which is now going to be delta triplet So now, what we need, because this is triplet, we're looking for odd parity, we need this guy to be such that when I expand it in angular harmonics, the V1 has a negative sign. All right? So let me look at what you would expect in the simple case of a ferromagnet. Somehow for a ferromagnet, what we would expect is that the potential is most negative on site and decays as you go away with some length. If I Fourier transform that, then as a function of Q, what I get is something that looks like this. Right? So it's again largest at Q equals 0, where the ferromagnetic instability is. It's negative, because you want it to have two spins aligned. And then it decreases as you go out to larger Q. All right? So now if I just start expanding this the way I did before, and I just look at the leading term, I have this. Plus. All right. So now you can see that if I want this guy to get bigger as I go away from aligned spins, this V1 is positive, but because the thing it goes with is 1 minus cosine theta, the first harmonic is negative, which is what you want. All right? So by this slightly convoluted argument, what you learn is that generically ferromagnetic fluctuations favor triplet superconductivity. Either attractive interactions favor singlet, S-wave singlet superconductivity, and anti-ferromagnetic interactions favor D-wave superconductivity. Right? Now, it's an interesting question that various people have pursued, how putting in interactions in the charge channel will change this, right? And you can see, because you're after these various harmonics, that you can imagine structured interactions even in the density channel that would favor D-wave superconductivity. Right? And similarly, you can imagine structured interactions in the charge channel that could favor P-wave superconductivity. I don't know of any natural models that give these, but you can imagine them. You can certainly cook up models which will do that. But the simple thing which gives you ferromagnetism is, which gives you P-wave superconductivity, is ferromagnetism. All right. So, that was all I wanted to say about the qualitative picture of getting superconductivity and how you associate superconductivity with different kinds of fluctuations and interactions. Right? Now, the big question left unanswered by all of this discussion is what on earth does a simple Hartree analysis like I gave you actually have to do with any real material, where there are a large number of complicated interactions, and the Hartree approximation is surely quantitatively completely incorrect. Right? So that's the thing that I want to turn to now on two levels. The first is to sketch for you the conventional sort of Fermi-liquid Migdal-Eli-Ashburg theory of phonon-mediated superconductivity and its extension to spin fluctuation-mediated superconductivity. And then I want to present in what's really more the most recent research results what we find by just taking a model and solving it numerically to the best of our ability, and that will be a statement about D-wave superconductivity in the covered model. Okay, so the electron gas and superconductivity. Okay, so if you just take a typical solid, aluminum, something like that, and you look more or less at electrons in the conduction band, right? You have a typical inter-electron spacing of some, which I will call A, which is of the order of, say, 2 angstroms. All right? So that gives you a typical kinetic energy which is, you know, maybe a quarter of a Rydberg or something. Typical potential energy, E squared over some kind of short-range dielectric constant times A. The ratio of these things, the ratio of the potential energy to the kinetic energy, is a dimensionless number. It's conventionally parametrized by saying that 2m E squared over h bar squared is the Bohr radius. I can put in this epsilon if I like. Then I have one factor of my lattice constant. So this is, in effect, inter-electron distance over some kind of Bohr radius, which is conventionally called R sub s. So basically, if R sub s is small, the potential energy is weak compared to the kinetic energy. So there's some kind of perturbation theory in the interactions. As R sub s becomes larger, you don't have a perturbation theory. All right. So basically, people have investigated this problem in great detail. I don't want to go over that ground here. Perturbation theory works well for R sub s about 1. Typical solids have R sub s of the order of 2 to 6, reasonably outside the region where perturbation theory works quantitatively.
Sorry, how do you say, why do you say perturbation theory is?
Oh, that's just, what I'm reporting to you is the conclusions of sort of 50 years of work actually doing perturbation theory and comparing it to other things.
What are those other things? It sounds like they're not experiments.
Or numerical experiments, if you like.
Okay.
But so there's two things. One is you can look at the next order and see if it's smaller than the one you started with. And the other is you can compare it to numerics, especially ones done by separately and later Drummond and people. But with the original conclusions, which go back to the early 60s, we're really just asking about the internal consistency of perturbation theory. Right? Asking, you know, you start the leading term, the next term, when does the third term get comparable to the second? Right? And all these things lead you to perturbation theory being decent only for RS of order 1 or less. Right. However, it's also true, if you do numerics, nothing fundamentally bad happens to the electron gas until you get to RS of 30 or something. You still have a more or less free fermion picture. All of the instabilities of just of the free fermion gas happen at much, much larger RS. Okay, now.
Gotcha. So I think this argument only works when the only interaction in the system is a long-range Coulomb interaction. If you have other type of interactions, then this simple comparison between K and PE doesn't work.
Good question. So there's two different ways to think about this. All right, but on one level, physically what you have is the long-range Coulomb interaction plus phonons, which we'll get to, right? I mean, the Coulomb interaction. E squared over R is the fundamental interaction between electrons, right? However, what's going to go wrong with the picture that the picture that I'm about to sketch for you goes wrong for several classes of materials, in particular transition metal oxides and heavy fermions, right? And the reason essentially is that this length scale becomes a poor estimate. If this is anticipating what I'm going to say, and I hope I remember that not to say it at the correct time, but basically, if you take something like a transition metal oxide, you take a transition metal D state, its size is half an angstrom, all right? The spacing between transition metals in a transition metal oxide is typically about 4 angstroms. You have transition metal, then oxygen, then transition metal, and somehow everything in solids are 2 angstroms apart. Just that's a rough So first, these guys are quite dilute on the scale of the lattice spacing. So what that means is that if I plot a charge density of the d electrons, instead of being like a plane wave, which is kind of this estimate, right? The actual wave function size is not set by this distance, but set by this distance. So if I plot the charge density, it looks sort of like this. Right? That's a caricature, but right? So the Coulomb interactions associated with the charge in these small spaces are not well given by this estimate. Right? So that's where this goes wrong. Right? And it's, again, you see that in heavy fermions, in transition metal oxides, in buckyballs, where the hopping between buckyballs is weak. And so it's things with a local structure that confine electrons, so that there's some kind of part of the wave function which is very far from a plane wave. That's where these estimates basically go bad. Yeah?
You mentioned that the quote instabilities of this
Yeah.
picture don't start happening until RS around 30.
Or bigger.
Are we talking about the ground state?
Yeah.
But I mean, Doesn't Cohn-Ledinger, for instance, mean that the...
Oh yeah, I'm sorry, but in instabilities which are at scales bigger than e to the minus 100 or something. I'll get back to Cohn-Ledinger, but that's a very, very weak instability.
It's tiny TC.
Yeah. Right. But I mean, where something, and you can understand, and I hope that we'll get to this. You can understand Cohn-Ledinger, and I'll explain this later for those of you who don't know. Basically, starting from this kind of picture, right? It's a tiny instability on top of this basic picture, right? The things I'm talking about are where this basic picture of more or less renormalized but still free fermion-like things fundamentally fails. Right, where you get something else, whether it's a charged Wigner crystal, a ferromagnet, or something completely different. Right?
What do you mean by good here? Here is good.
It's a reliable guide to the physical property. It's a reliable and even quantitatively reasonable guide to the physical property. So if I want to calculate something, I know which interactions to include.
But if ground state is similar to...
Well, that we can discuss. That's where I'm going with this. But the statement is that perturbation theory, in its simple form, is not good. In this precise sense that higher order terms appear to be as important as lower order ones. And I want to emphasize that this is particularly important for superconductivity, for the reasons that I said last time, right? These simple BCS Hartree approximations, right, are in a sense saying, all right, I have a wave function. Now I'm going to make, of some kind of, which I can view as a variational wave function. Now I'm going to add a variational parameter, which is this pairing correlation, and see if the energy goes down, right? Almost always it does if you do a careless calculation, right? So, or I'm going to take some residual interaction and do a second order perturbation calculation to see if it gives me superconductivity. Again, second order perturbation theory almost always lowers the energy. So it's very easy to find superconductivity if you take a complicated system and pick out one part of the interaction that you like. So to really make a reliable statement about whether you get superconductivity, you have to be sure that you're capturing all of the interactions that are relevant to the problem you want. Right? And that's why you need either a controlled perturbation theory or some kind of good fixed point understanding, or a well-defined model just with a reasonable numerical solution. Right?
So,
I'm sorry, yeah.
I have a general question. So why does the perturbation theory usually works pretty well, even in the region over which the perturbation theory cannot be justified? For example,
you
like
mean, how can we say anything intelligent about this region?
yeah, like even
I'll
for
come to that.
yeah.
That's where I'm going in the next 20 minutes. I haven't told you yet, but I plan to.
I mean, for the large N theory.
Just bear with me. Bear with me. All right. That question has not been answered yet, and I'm going to give you a partial and qualitative answer.
I'll wait.
Okay.
Question. Can I ask you to repeat what happens at RS goes up to 30?
Oh, yeah,
I missed
yeah.
that part.
Basically, the obvious instability is the so-called Wigner crystal, right? There's another ground state I could make. This is basically perturbation theory around the free fermion ground state. So it's saying that basically what I have is plane waves, right? Which are, renormalized. In some ways, basically I have plane waves. The alternative is I could start by making the potential energy happy, right? That means I just localize the electrons, putting them as far apart as possible. That's the Wigner crystal state, right? And that happens at a really big RS, at least according to all the numerics. 30, 40, 80. It's not an easy state to find. It's very easy to melt the Wigner crystal. And notice, by the way, it's not really important here, but the scaling is kind of opposite, right? Because of the long range of the Coulomb interaction in the 1 over R, high density is weak correlation. Okay. So anyway, the basic question which you asked is, all right, how can we make any intelligent statements about real solids at all, given that we're well out of the perturbative regime? All right, and there are really 3 steps to the argument. The first is screening and Fermi liquid theory, right, which is basically a, if you like, self-consistent justification for saying that with some corrections, which we can discuss relatively precisely, the properties of there is a fixed point of the theory of interacting fermions, which has all the qualitative behaviors of non-interacting fermions. Right? The second statement is density functional theory, which I think I'm not going to have time to talk about. right? But which turns out in practice for many systems to be a very accurate way to calculate properties of that fixed point. And by very accurate, I mean within, 20, 30%, which is remarkable for a strongly interacting quantum problem. All right. And the third thing is so-called Migdal-Eli-Ashberg theory, which is, if you like, a systematic expansion in fluctuations around a ground state, which you don't have to understand precisely. So it's a combination of those three things, which for conventional materials works reasonably well for reasons that I'm now going to try to describe to you. And again, where this goes bad is these kind of situations where you have strongly localized states to start with.
That's kind of in favor of us, right? Because the kinetic energy gets greater than what you would expect.
But not really, because the part of the kinetic energy that you care about is the part which takes a carrier from here to here, right? There is, there's some kind of balance of kinetic and potential energy which gives you this wave function to start with. That's like solving an atomic physics problem, right? Then it's what you do with that. Right. So if that hopping is small relative to the correlations.
I see.
Right. But it's that the basic wave function looks like this and not like a plane wave. That's why these arguments go bad. All right. But now let me give you these arguments which work for most known things. All right? And so I'd like to begin with the simple consideration of this small RS limit. So let me just talk about free fermions with the 1 over r squared interaction, 1 over r interaction. And now let me just Fourier transform the Coulomb interaction. So instead of having e squared over r minus r prime, I Fourier transform it. The Fourier transform of 1 over r, as you know, in 3 dimensions is 1 over q squared. So we have something like this, all right? Now, I said that in the small RS limit, somehow you have a perturbation theory, right? But you see from this that there's something rather peculiar about this perturbation theory, because although generically, if I evaluate this at a scale corresponding to an inter-electron separation, the potential energy is small compared to the kinetic energy in the dense limit, right? There's a region of momentum space where this becomes arbitrarily large. Right? This 1 over q squared means that there is some momentums for which this is very big. Oh, it's over here. Okay. So what that means is that it's important to screen the Coulomb interaction, right? So that if I consider a process which I might draw like this for two electrons interact, an electron interacting by the Coulomb interaction with another electron, all right? At small q at least, this line becomes large, so that therefore this contribution can be bigger than the one I started with, and this contribution yet bigger. Right? So there's a series of diagrams, if you want to think about it this way, that pick out the divergent term in the Coulomb interaction, right? And which sum up into a geometric series. So if I define this I will call it chi, and it's basically the electron density-density correlation function because the Coulomb interaction couples one density to another. Summing up this series says that I have an effective interaction which looks like this.
Sorry, you just said that we were working in a regime where 4 pi, where it gets larger as you increase the bubble count. Doesn't it not convert there?
I'm sorry, say that again? I just didn't.
This geometric series has a radius of convergence, right?
Ah, yes. So I think that basically, what I'm going to give you is the physicist's answer that this all works. And that's back to this. But basically what you'll see is that because this sign has a minus here, it has a non-convergent thing on the opposite half plane. And there's this whole story, which I don't really have at my fingertips, of Borel summability and things like that, which say that even though there's a pole very close to the region that you're looking at, but on the other side, the series in fact behaves as though it converges. Right? Basically, when you sum this up, you don't get any divergences. It sums up to something small. If I change the sign of E squared so that the coupling was negative, there would be a divergence somewhere. So there's a horrible non-analyticity as a function of E squared. Right? But professional mathematicians have sorted that out, or professional field theorists, and you don't have to worry about it. Right? Anyway, the magic words are Borel summability, and the person who worried about that, to my knowledge, was Edouard Brezin. All right. Now, small r sub s means that if you don't have this divergent thing, then you don't really have to worry about interaction, other interactions. So diagrams like this, where the small q doesn't play any privileged role, where you just sum over these q's, right? You don't have to worry about, at least in the small rs limit. Right? But this you need to do. Right? And this has the physics that we all know and love of screening. And actually, let me just interject here. So I started at 3:45, so I think I should stop around 5:15. Is that right? Okay, so I'll organize things to come to a reasonable stopping place at that point, at that time.
Excuse me?
Yeah.
Can you please repeat the argument why this RPA series for psi is important while other diagrams you can ignore?
Yes. You can see it from this geometrical structure. Basically, there's a certain region of momentum space where q is small, where this interaction becomes arbitrarily big. Right? Our original argumentation over here was based on evaluating the potential energy at a distance of order the interparticle separation. Right? In other words, if I say that q is like 1 over a. Right? So if I take q's which are much smaller than that, this interaction becomes much bigger. All right? So that's statement one. Statement number two is this series of diagrams, right, privileges that small q, because at every step I have the same small q flowing through my interaction line. Other diagrams you can imagine, like this one I erased, inside here the rules of diagrams say I should integrate over this momentum transfer. So I don't get a 1 over q, I get an integral in 3 dimensions of 1 over q. Right? So it's not divergent. And slightly funny things can happen in 2 dimensions, where you have, well, it's d2q over then it's over q to the power 1, and peculiar things can happen in 1 dimension, but I don't want to go there. Yeah?
You didn't just tie to the fact that free Fermi gas is compressible, and every one of those bubbles gives you a constant, and every one of the wavy lines gives you one of the
Yeah, well that's what this
But
says.
if it was incompressible, then in fact there would be nothing special about this series.
Yeah, right. So, in fact, here I still, as Oscar said, have to say what this is. Right? Because as you said, basically, if the Fermi gas is incompressible, that means that it doesn't respond to changes in potential. Right? And if it doesn't respond to changes in potential, then this interaction, which is basically you make a density fluctuation here, it makes an electric field, it causes something else to happen, will do nothing. Right? But as we know, electrons flow to screen charge. All right. So we can calculate this thing. All right. This is a response function. All right. And in the interest of time, I'm not going to give you the calculation. I'm just going to tell you that at small, well, you get a formula like this which has the interpretation that what's inside here is in response to a perturbation, which changes the potential, you excite an electron from a filled state in the Fermi sea at some momentum to an empty state at a momentum p plus q, or you do the reverse. And this is the energy denominator for that process. Okay. So basically, you take an electron out of the Fermi sea, a filled state you take an electron out of a filled state in the Fermi sea, you put it in an empty state. Right. So you can evaluate this at small wavelengths, writing this, so that if q is small, I can get the energy at p plus q relative to the energy at p by taking the derivative of the energy with respect to p, that's the velocity, and dotting it into my momentum. All right? So if I do that and treat this Fermi function slightly sloppily, this becomes, I take the derivative here, I get my difference in energies here, and this. All right, so now there are two things that you see. First, at small frequency, I can neglect this. This factor cancels this one. This is just the derivative of the Fermi function at the Fermi surface. This just gives me the density of states. All right. I have one minus sign from here, one minus sign from here. The Fermi function is 1 inside, drops to 1 outside, so it's a negative delta function. So overall what I get is minus times the density of states at the Fermi level. So that means that if I go back to here, I say that this. So now if I multiply through by q squared, I get this. By the way, there should be a factor of 2 here because I have 2 spins. So let's interpret this as the total density of states from both spins. Right? Now, let me multiply and divide by this density of states. All right? Because this thing is an energy, this is a density of states, it's an inverse energy. So this has the interpretation of a wavelength. And what it is the Thomas Fermi or screening wavelength. So I could rewrite this like this. So what this says is that basically after I do screening, my interaction is replaced by something which is of the order of 1 in appropriate units. It's just 1 over the density of states times a factor, which is 1 at small wavelengths, shorter than this QTF, and then goes to 0 for longer wavelengths. So what you should think about for the electron gas, all right, generically, is that the basic Coulomb interaction after you take screening into account, is just of the order of 1, with momentum dependence only on this scale. Furthermore, if you put in these numbers, 4 pi e squared is typically large. So what this says is that the Thomas Fermi wave vector is large or the screening length is short. Typically in solids, it's of the order of 2 angstroms or less. So on any scale that you care about, the Coulomb interaction is just screening. All right? And that qualitative conclusion is correct even at larger RS. So the basic picture is you start with this strong long-range interaction, and screening converts it into something which is of the order of 1. Now, things which are of the order of 1, of course, still have effects, but it's not horribly divergent. Now, I'm sorry, was there a question or a remark?
This is the static part.
This is the low-frequency part. So next question is to ask about the frequency dependence. Yeah, here.
I'm always worried about this because, as you know, in the legitimate formulation of Landau Fermi liquid theory, you have to include a long-range part to the interaction, the Landau parameters. You can never get removed until you resum the diagrams. And so,
yes,
so there is some issue there about whether you can
let's come back. Let's come back to that when I get to Landau theory. Basically, what that is going to do is do funny things to the long wavelength density response. All right, but at typical momenta in interactions, what you have is things of the order of 1. Right, and we'll see the way things are going. Probably not until tomorrow. Where this long-range part of the interaction comes back to bite you. But it's nothing very bad, right? And it's basically because this is very short, because 4 pi e squared in natural units is big.
Do you think it could become an issue at a quantum critical point?
Well, it depends which channel it couples to, right? Once you go away from the long-range charge response, all you have to do is say that you stay screened, and everything works fine. Right? Now, one of the things this says, actually, and again, I'm going to run out of time here, is that at long scales, if you actually continue this analysis and compute the long wavelength physical density response, what you discover is that the actual density fluctuations at long wavelength are strongly suppressed. Right? That's a statement that what the electron gas wants to do at essentially all costs is preserve charge neutrality. Right? Now, what we'll get to, and I certainly don't have time to wake up my computer now, so I'll show you tomorrow, is that if you talk about real solids with lots of bands and lots of degrees of freedom, for everything except the details of the plasmon, which I'll come to, all of this screening and adjustment happens by transitions involving filled bands. Right? So that in practice, things that you don't really care about readjust themselves so that the total charge stays neutral. To give you a concrete example, and now I apologize, I'm going to run over by about 3 minutes. There's a lot of discussion in solids of charge order, right? Where you take a material, for example, lanthanum nickelate, right? And it behaves in many ways as though on one side the charge is big, the next side the charge is small, the next side the charge is big, right? If you do any realistic computation and you really compute the charge density, what you discover is that the charge density, the physical charge density, is essentially uniform. It has only very small modulations. If you look at the charge associated with conduction bands, with orbitals within a half an eV of the Fermi surface, you see a substantial modulation, right, which is almost completely compensated by shifts of the charge density coming from filled bands from the other atoms, from, if you want to use this jargon term, rehybridization. Right? So another way to say it is that all the energy scales associated with this are big. So the charge just readjusts itself to do what this tells it to do on scales that you don't care about. All right. So let me think. I have to figure out a sensible way to wind this up. Where did I get to? Oh, yes. So I think the last thing I should say about this is the frequency dependence, right? This was essentially a quasi-static calculation, all right? Now, where does this thing go wrong in 3 dimensions, right? To get an estimate of the frequency scale where this thing goes wrong, let's look at the opposite limit of high frequency. All right? If I'm at high frequency, then I keep this in the denominator, I neglect this. This factor averages to 0. Right? So therefore, at high frequency, I get this, right? The leading term is 0. I have to expand to 1 order in VQ over omega to get something which is not 0. So then there's an angular factor involving averaging this over the Fermi surface that I don't want to write, right? But so you get something like this. So now the sign is plus. If I go back to here, what I see is something which has a denominator which is 1 over 1 minus 4 pi e squared over q squared, density of states, Vf squared, q squared, over omega squared in 3 dimensions. The q squareds cancel, and we can write this as omega squared over omega squared minus some frequency scale. Right? So there is a natural frequency scale in this problem where charge oscillation happens. That frequency scale is called the plasma frequency, and it's again determined by this combination, 4 pi e squared and naught Vf squared. Right? And basically, these static arguments I gave you go wrong when frequency gets to be of the order of the plasma frequency. Right? So therefore, you should ask, how big is the plasma frequency? And again, because 4 pi e squared in natural units is a big number, this is typically big compared to the Fermi energies that you care about. So typically, you get all electron plasma oscillations in solids at frequencies of the order of 10, 12, 15 eV. And if you're at scales below that, then things are screened. Right? Now, of course, you will still have, if you have a conduction band, you will have a plasmon excitation associated with that. Right? But it doesn't make very much difference for practical purposes. The basic plasmon that you care about in solids is connected with essentially all the electrons and lives at a high energy. And if you're below that, for most purposes, you can think of a screened interaction whose strength is of order 1. So that's the basic idea why you can start to formulate a sensible description of this regime. And then what I want to do next time, what I wanted to do, what I want to do in the next 20 minutes of today, is sketch for you a sort of renormalization group argument that starts from a picture of short-range interactions of moderate strength, right, and shows how they evolve to do essentially nothing. That is the renormalization group derivation of Fermi liquid theory. And then I'll explain in a little more detail what essentially nothing actually is. Right? But the things that you should remember from this are that the plasma frequency is big and the screening length is short. So stuff just adjusts itself to make the long-range Coulomb interaction happy. And then you should consider physics after that, just with the constraint that everything is adjusted to make the long-range part of the Coulomb interaction happy. And for most purposes, that adjustment is done by this rehybridization, just rearranging things in filled bands that you don't really care about. Andre.
Very simple thing, repeating what Pierce asked here. Suppose you are close to critical point,
Yeah.
which is Q equal to 0 critical point, but only small Q fluctuations are relevant. You were arguing that frequency is irrelevant when it's smaller than plasma frequency.
Yeah.
But there's also a scale BFQ, and Q is small. Well,
So let's
the interaction definitely changes.
So when you come to critical points, it's different. The statement here is just that the particular Coulomb interaction doesn't do that. One way to say it is that you don't get critical points that involve long wavelength modulations of the charge density. Those are frozen out. We can later discuss what happens at small q, or at any q, if you're near a critical point or in other circumstances. The basic point here is just that the strong charge interaction screens itself and leaves behind a footprint of order 1. right? The screening happens, and the screening happens on the scale of the plasma frequency. So there's a couple of cases where this will go wrong. All right? So I'll show you next time an interesting plot of the screen of the effective Hubbard U, which will make this point nicely. But there's two places where this goes wrong. All right? One is this, where you have strong short-range interactions associated with packing things into a small space. All right? The other is cases where the density of free fermions is very low. So in particular, doped strontium titanate is a superconductor with a very low Tc and a very low Fermi energy. Right? And it's interesting. It also has all kinds of funny business with its dielectric constant. Despite that, people have estimated for doped strontium titanate all of these scales. All right? And what you find is that the Fermi energy for typical dopings that maximize the superconductivity is 10 or 20 millivolts. The plasma frequency is 5 or 6 times that. All right? Correspondingly, the screening length is comparable to the inter-electron separation. Right? So these 4 pi e squared has a profound effect on the physics that on the physics that we're interested in. Right? So with that, I'll stop and pick up first thing tomorrow.